doable, of course, but I'm not sure we might be able to carry everyone along while doing that. So let's look at condition generation together. So I think earlier on we looked at language models and how they can be used to how they can be used to generate text. I think in particular, the one thing that they wanted us to keep in mind was that language models are a way to model a probability distribution over maybe plausible sentences or documents in one particular language. And yeah, so we have something like this. We have this probability distribution over sentences or over documents. But when we go to conditioned languages, um, in addition to generating sort of using our probability distribution, we want to condition that generation using a particular specification. And that specification can be a lot of things. It can be structured data, which we'll see later on. It can be a particular language, in which case we are going to generate another language. It can be a document, in which case we are going to generate a short description. It can be an utterance, in which case we are going to generate a response. It can be an image, in which case we are going to generate a text, or it's can be speech even, in which case we are going to generate transcript. I think that even on this course, I think it's possible to enable this condition generation because I know that Zoom has Zoom has this transcripting where it can automatically convert what we say to a caption that we can all read. And for each of these different types of condition generation, or let's say these different specifications, they are named different tasks. For example, if you are conditioning on speech to generate a text that's speech recognition, and an image to generate a text that's image captioning, utterance that's response generation, conversational models, a document to short description as summarization, and maybe one that we hear about a lot in Masekani from one language to another, that's translation. And we start to look at how we can formulate this conditioned generation. Previously, I think we should all recognize this particular probability. In this particular one, this one we looked at when we're doing language model, we try and to calculate the probability of a sentence, we say that for every particular word in that sentence, let's condition it on all the previous words before it that has been generated. In which case, for each word, we're trying to condition it on its context, right? But when we get to conditioned language models, we have an additional context. So in this case, we're not just predicting the probability of X, that's the sentence. We're predicting the probability of, in this case, sorry, we'll move the sentence now to Y, given an X, where the X is our added context. So if you see, is there a way for me to yes. So now we can compare both probabilities and see that what has changed is that we've added an additional context on which we are conditioning the selection of our next token. So whereas in our previous discussions of language models, we just found for to calculate probability of a sentence, we just did multiplication through of the probability of each particular token given every context. In this case, we do that not just on every context, every word that comes for it, but also on our chosen additional context. So in this case, this could be image and then whatever else has been generated, or this could be speech and whatever else has been generated. So that's the way that we might condition, our generation. But I think more okay. What type of language model? And what do we achieve by doing this? Yes. So we look at Mikolov et al., which I think this is one that we implemented last week during our code walkthrough. And in the next slide, we look at how we might employ it in conditioned generation. And they show one way to do that, and that is to have we still have the same architecture as before, but now you can see that the output from the last state is now fed into a second kind of machine. It's exact in this particular case. The exact same type of machine is just duplicated, but the output from this first part, which they call an encoder, is then fed into the first hidden state of the decoder, which is exactly the same. Let me use machine. Exactly the same machine. So we have an encoder decoder architecture, and that's influential work by Sutskever, which is a very interesting paper to read actually. Okay, so we still have, in this particular case, is simplified because we still have the same machine, and what we are doing is we are conditioning the generation, which is happening here, in the decoder. We are conditioning it on the output of our encoder. For this particular instance, we are doing that conditioning by feeding in the output of our encoder to the first state of our decoder. But I think there's a number of ways we can do this passing of the hidden state. And one of them is to initialize the decoder with the encoder. That's normally when we start, when we start our models, as when we build a model and we want to start training, we have to initialize. I think, like, was it 2 weeks ago, we discussed a number of ways we could initialize models. I think we discussed there was an Xavier normal. Then I think there was a normal. There was just normal. Then there was uniform. I think we discussed like 3 different ways we could initialize our models, like 2 or 3 weeks ago. So in this case, now we just initialize our decoder using the outputs of the encoder. And of course, this assumes that the decoder and the encoder are of the same dimension, because if they're not the same dimension, then you can initialize with it. But in case where they're not of different dimensions, you can perform some kind of transformation before using it to initialize your decoder. And in this case, by Blunsom et al., we have where the encoder output is fed at every time step. So that's another interesting way. Of course, this is a lot more computationally intensive. And I wonder how much gain in performance they did from doing that. Methods of generation. Okay. So let's hear Shamsuddin now. Shamsuddin, you said you had time to go through the course material. Did you encounter anything interesting while exploring generation?
You say what?
I said, did you encounter anything interesting while exploring this section of last week as methods of generation?
I can't say anything about
that. Let me see. Is there anybody else? All right.
I think apart from this slide, I have not had anything to add.
Okay. All right. So so we've looked at how we can model our generation. We looked at how we can model the probabilities of our sentences, and but in generation, there's a number of ways that we can achieve that. And in this particular section, we start to look at the different ways that you can approach generation. If you remember before, we showed the probability distribution. I think earlier on also we showed how the final layer of your the final layer outputs probabilities using the softmax. I think we also discussed how the softmax is computationally expensive and ways that we can either approximate it or reduce its let me say expense really. Yeah, I think we had class-based softmax then and one other type. Yeah. But we've shown that the output usually is a set of probabilities, and in generation problem we look at how we can go from those probabilities to our sentence. And one way to do that is to sample. That is, at every time step we have an output probabilities. Why don't we sample? We sample a particular token according to the probabilities that is outputted by our probability distribution. And the second way that we can approach is to just argmax, in which case we just take at each time step, let's just take the word that has the highest probability. So these are 2 different ways that it's not exhaustive, I think, but there are 2 different ways that we can approach generating at every time step. So first, this one is ancestral sampling, and I think we should all recognize this symbol from last week. This is the end of sentence symbol that we used. And we say that, while we've not generated our end of sentence symbol, let us sample a token or a word according to the probability that that our model, our model outputted, and that's all. So I think maybe when we compare it to argmax, we can see how sampling can be a lot more unpredictable, because you know that if you have, I'll explain it. If you have probabilities 0.5, 0.3, and 0.2, and we say let's sample from it, it doesn't necessarily mean we're going to pick 0.5. We might even end up picking the one with the lowest probability. That's, of course, if we did it once. If we did it multiple times, then it might converge to the probabilities that we mentioned. But if we do it just once, and then move on to our next time step of generation, you can see how sampling introduces, let me say, sort of non-deterministic. It's a lot more surprising than if you just simply took the one that has the highest probability. When we use argmax, where we just pick the word that has the highest probability, it's similar, except that rather than just sampling from the probability distribution that we obtain, we just take the argmax of it, which means that we pick the word at the token at the index that has the highest probability, and maybe I think maybe let me see if I have something for this.
But Tunde, what is the problem with that sampling? We have just finished.
I wouldn't exactly say a problem. So one thing you'll find is that when you're working with decoding, it's about what exactly are you generating for? Because, for example, if I remember correctly, the sources of GPT-2, some of the sources of GPT-2 as a storyteller is attributed to performing sampling. Because, like I mentioned, sampling is a lot more surprising than you might than you get when you use when you use greedy search, which uses argmax. And I think I have a script here which maybe can help us demonstrate it. I'm not too sure. Let me just try it out. Just connect. All right. So in this particular case, I'm using I'm not using GPT-2. I think this particular document uses download GPT. So this from let me just share this. Give me a moment. Oh, I could have done that easily. Chat. All right. All right. So this is based on Hugging Face. All right. So okay, I think the data is connected now. Let me just install transformers and yeah. All right. So we import if we install transformers, then I'm just going to load just import the usual libraries. Like I said, I want to use GPT-2 LM models to just try and demonstrate the difference that we have. And you can see that I'm using Microsoft Dialog GPT Small. So Microsoft Dialog GPT Small is a conversational model that was trained from GPT-2 itself. So if I load these guys, okay, so let me just gloss over this. This is we have a generate function, and I'm going to prime our generate function by I'll pass in a model and tokenizer and just leave our prompt. So the prompt is something we're going to pass into pass into the model, and the model is sort of supposed to reply. So this is also condition generation, because in this I'm conditioning it based on a particular prompt, and then it's supposed to respond, generate something in response to that. Okay, so now I have that. So I can start by just going straight up. And let me just do like this. Yeah. So the way that it works is if I don't set what about generation happens, what then it's greedy search that happens. So you can say for greedy search, for example, we have, I'm not sure if I'm missing something. That's what the model generates in response to try this cake, I baked it myself. But we can look at Beam search. Well, first let me go to sampling because we have not looked at Beam search in on the slides. Now for sampling, we can say so when we are doing sampling, actually, there's a number of things to keep in mind. I mentioned that in sampling, we want to sample a particular token at every time step, according to the probability that outputted by your model. But like the probability distributions can be of different shapes. You can have left skewed distributions, of course, in which case you have like a lot of your probabilities concentrated on a few words. You can have something that's a lot more uniform, in which case, it's almost even across, or you could have something that's sort of like a normal distribution. So you want to really control when you're doing sampling for generation, how your probability distribution still affects how your sampling is done. But there's a way that we can impact the probability distribution of the model, and that's using temperature. So when you raise the temperature of your model, the temperature of generation really, it's called the softmax temperature. When you raise the softmax temperature, what happens is that you get the softer probabilities. So rather than having like a lot of your probability concentrated on let's say there's only two particular classes, let's say there's only A and B. Let's say previously, your probability is only 0.9 and 0.99 and 0.01. If you raise your softmax temperature, it can soften those probabilities. So we have something like 0.75, 0.25. So these are much more softer probabilities than you normally have obtained. And, it affects the way that your model can sample because it affects the probability distribution. So you can set a temperature. You tell the transformers that you want to do sampling. But there's other types of sampling also. There's top case sampling. So we have to specifically set top case equals to 0. And let me start by not even specifying a maximum length and see what we actually get. Yeah, so we have sure, why not? And this is a lot more interesting answer than we got from using Beam search, right? And if I run Beam search again, if I'm right, we should still get the same. We still get the same prediction. But if I'm right, where is it? I hope I already seeded it. All right, let me see what happens. But if I'm right, every time we run sampling, we should get a different. A different generation. So it's like a cake. It says I don't get it. So you can see that there's a way that sampling number 1 is non-deterministic, and its prediction is a lot more surprising than you might have with your if you are using greedy search.
So Tunde, this is temperature sampling in that way, right?
Sorry?
This is temperature sampling.
No, it's not temperature sampling. Temperature is used across board, really. This is just like normal sampling. It is simple sampling. Let me call it simple.
Okay, but I'm not sure whether we do also have temperature sampling where we, like in this top K sampling, you can see we only provide the top K, but this temperature sampling is not provided. So you cannot combine, I think, the temperature and top K, because I'm not sure there are different sampling techniques.
I can. Like I mentioned before, what you do with temperature really is to affect the way that your probability is distributed. I think that these guys have a graph that actually shows that. Let me see. Sorry, just give me a moment. Oh yes, I think it's somewhere here. Or is it this one? I think it's here. I'm not too sure. Yeah. So I think the way that it's not the exact graph, but maybe it can just illustrate it. I think the way that you might think of temperature is the fact that when you use softer temperatures, you are less likely to get when you raise the temperature, you're less likely to get cases where your probability are concentrated in like a few tokens, they would probably be like a lot softer, like this guy on the left. Do you understand? So it doesn't matter the type of sampling that you are using. You can decide to raise temperature or to lower the temperature to
So,
help you.
so what about lowering the temperature? Will it make the models more confident? I mean, if we use like something greater than 1, or the range of usage, because there we use 0.7, right?
Yes,
So what makes the models more confidence in terms of the temperature, the
lowering
lower
the
temperature or the greater the
lower
temperature?
temperature, you get sharper probabilities. If you increase the temperature, then you soften it.
Okay.
Sure. So that's what's occurring there.
Sorry to me. So does temperature in any way affect beam search? Because
Beam search.
thinking of how, yeah, beam search, thinking of how the sentence you end up selecting in the long run when you are doing beam search is the one that has like a collective higher probability than the
Yeah.
rest. So when you are applying temperature and then it affects like the output of the softmax,
Yeah.
where originally you might have like a sharper output where one class has more, the probability is higher than the rest, like significantly higher than the rest. But when you apply temperature and then it becomes closer, does that in any way affect beam search? I don't know if you get what I'm trying to say.
Yeah. So I think let's introduce beam search before we start discussing, the kind of troubles that can occur around beam search. So first of all, we discussed greedy search. In greedy search, we say we use the argmax of the probabilities, and that just means that at each time step we select the word of the token that has the highest probability. And going by this graph, in the first case, we selected D, and then we selected nice because we have 0.5 probability, which is higher than dog at 0.4 and car at 0.1. So we have the nice. And then from there, we select woman because it has a higher probability, 0.4, compared to house and to guy. So we have the nice woman. But there's issues that can occur, for example, when we generate this way. And one issue especially that you can imagine is, what if like a better sentence is hiding behind a word with low probability? Like for example, let's say for example, the something like the dog has, we can see that has about 0.9 probability, and it might be a lot more interesting sentence depending on what context we are generating on conditional generation on. So that's one issue that greedy search has, is that sometimes a better prediction, a better generation is hiding behind a low probability token. And because you only select the maximum at each particular point, you miss out on such sentences and you generate only generic sentences. And also because like common words are likely to have higher probabilities, and it means that the vocabulary that your model eventually uses is small, and it whatever it generates is not very surprising. It uses common words. But one way that we can get around that is to use beam search. For beam search, what we do is that rather than just taking the maximum probability at each point, we decide how many maximum probabilities, let me say it that way, we want to take. So if we say we want to take 2 maximum probabilities, that means that at each particular generation point, we keep track of the 2 highest probabilities. So in the case where we get to D, before we are taking just nice because nice was 0.5. But when we start using beam search, we keep track of nice and dog. So now we have the nice and we have the dog. And then we look at, okay, what are possible next tokens? And then we have the, and runs and has, we have woman and house and guy. And then we pick, okay, what are the top 2 highest probabilities? And at this point, we have the dog has and we have the nice woman. So you see that this allows us to track multiple paths until we can eventually reach an end of text token where we pick the sentence that has the highest probability. So it allows our generation to be, smarter really, by not falling into a loop where we just pick the most common, the most probable sentence, which might not be the right answer. So usually, when we are working with beam search, we do not alter the softmax temperature, because altering the softmax temperature is orthogonal to the way that that beam search works. Because when you alter the temperature, you affect probabilities, and you make probabilities a lot more softer. So you end up in cases where you can't keep track of what are the highest ones, what are the highest paths I should follow, because you have raised, for example, the temperatures and affected the way that it's distributed across them. So usually when you're working with beam set, you will seldom alter temperature. It's usually when you're doing sampling that you alter temperature. Does that answer you?
Yeah, that makes sense. I mean, as long as it's not happening.
So let me see. I think next the beam search actually comes next. We've looked at the problems with beauty search. You picked the easiest words and the most common words are picked. So for beam search, we look at how instead of picking the highest probability words, let's maintain a number of paths and then follow them through until we can find a sentence that has the highest total probability, which we then go with. So like I mentioned, there's an encoder decoder. What's it called? There's an encoder decoder script, but it's in DINET, and maybe as against next week, we'll try and see how we can convert it to PyTorch. So next, we look at model ensembling and the different ways that it can be done. The simple breakdown is for model ensembling, we are looking at combining predictions from multiple models. And one reason that we do that is because if you have multiple models that have different characteristics, then the errors are usually uncorrelated. And then if you combine predictions from these different models, it means that you can compensate for whatever errors that any single model is making using predictions from the other model. I think this is very common, for example, on cargo. If you can ensemble multiple models that are performing really well to obtain a model that is less likely to overfit and drop you on the private leaderboard. So, and then we look at different ways that you can you can ensemble model, because we already mentioned in ensembling, we are combining the predictions of different models, but how exactly are we combining these predictions? One way is to use a linear interpolation. And so we should recognize like this half of this particular equation. I think it should be the left half. Yes. So the left half is the normal probability that our model generates, which we looked at earlier. And then the right part really is just the probability of using the model M at any particular time step. Yeah. So at any particular time step, what's the probability of using models M's predictions? So we have a sum over all your models of the probability that they output and the probability of using them. So in essence, this can be simplified as this entire probability on the left, if you just collapse it into a single variable, like let's say A, and you collapse everybody on the right to, let's say, I don't know, let's say B. So in this case, this is just a summation of like A times B, where A is the probability distribution that your model outputs, and B is the probability of using your model at this particular time step. And it's common to set the second term to 1 over M, where M is the number of models that you are considering, in which case you're just as likely to pick any of the models, right? And another way is to use the log linear interpolation. In log linear interpolations, it's still similar to before. If you can see on the right side, this is the probability that our model always outputs, and we take a log of it, and then we have the log of and then we have what's it called, the probability of using the model at any particular time step. But in this particular case, we don't use probabilities anymore. We just add an interpolation coefficient, which we have here. And then we take a summation over all the models. But by the time we start using log linear, there's no, what do we call it? We are not guaranteed that our probability will be well formed anymore. When I say well formed, that means it's going to be between the ranges of 0 and 1. Once we take log, we step out of that realm, but we still need our what's it called? We need our outputs to be as probabilities. So we take a softmax again after. So it's still same thing as before. Here's what our model generates. We take a log of it. We had our interpolation coefficient. We sum over all the models that we have, and then we take a softmax. And once again, our interpolation coefficient is always set to 1 over M for everybody. That's assuming that we're as likely to take any of the models at any particular time step. And we look at intuitions of the way we can think about linear and log linear. And we say that our linear is basically a logical OR, a soft logical OR really, because you're not exactly picking one or the other, you're just combining them in ways sort of. Yeah, but what we find is that if you use the linear model, then it favors confident models. That's at any particular time step, the model that has a higher probability is going to push n token to be used. So it allows you to models that have different traits or that capture different traits. Say a model is better at capturing color than it is at capturing shape. If you combine them, for example, then you have a model that can capture what's it called, shape and color. So they have different traits. They can they have different characteristics that you can combine. And they say it's necessary when a model can assign zero probability, and that's because if you look at what do you call log zero, it's going to be an issue here. So whenever we are sure that a zero can actually occur, it's better to use the linear model. Then they say log linear really is like a logical and. Just check where the models agree, and it's what it pushes through for you, and it allows you to restrict possible answers. So if I remember correctly, they say it's better to use log linear, for example, where you have where you're dealing with sensitive decisions. You want to make sure that you are sure about this decision that your model is helping you make, and using a log linear helps you do that because it's where all the models agree that we move. But I think that there are other ways to approach to combine multiple models apart from combining their predictions. For example, we can look into their parameters in what we have as parameter averaging, and it saves us one issue. In fact, at test time, for example, we don't have to make predictions using multiple models, so that saves us. It saves us time, it saves us storage, it saves us some computational complexity too. In terms of how many calculations we need to make a prediction. So what happens here is that we just find a way to average the parameters of all the models in our ensemble to get a final model that we then use. Usually like towards the end of training or at the end of training. So it allows us to get that single model that averages the different parameters of all the models in our ensemble, and to get that final model that has should I say that it's in between, as all that can exhibit all their characteristics. So that's then there's distillation, which is dear to my heart. So in distillation, this is the work of Kim et al. In distillation, we need to find a way for all these ensembles to act as teachers for one particular model, which we might call the student model. So in ensemble, we want to find a way, in distillation, we find a way for the ensemble to act as teachers and to distill their knowledge into a smaller model, which we call the student model. And usually when we are doing distillation, once again, we reach out to the softmax temperature. So what we do is we want ideally, how do I explain this? The reason we work with surface temperature again when we're using distillations because we want the student model to be able to understand where teacher models are a lot more confused rather than where they are certain. Because there's a lot more information contained in understanding that our model is likely to confuse the digits 8 and 3 than telling this that our model is sure that this is an 8. So if you can help our student model to see that the digits 8 and 3 are easily confused, the model learns more than if you just start telling that this is the digit 8. So that's what we use softmax temperature for here also. So usually we'll raise the softmax temperature and try and get a single student model to learn from these different the models in your ensemble. So I think the biggest issue when you're working with distillation really is finding a student model that has enough capacity, or should I say the right capacity, to be able to learn the characteristics that the models in your ensemble have. But distillation is still a very interesting tool to keep in your arsenal because it solves one of the problems that we have with parameter averaging. Is the fact that we can only use parameter averaging with models that were created from the same run, and that's because of that I think that was like at the beginning of this study NLP in one of the first two sessions when we looked at I think that's when we looked at continuous bag of words, and I think Odo was one that raised the question around I think that's when we looked at how we might use it to classify a sentence or so. Is it a sentence? To classify a review or something like that into positive. Is it that positive or negative or strongly positive, positive, neutral, something like that? And then we looked at, I think in that case, we chose the dimension of 5 for our model, and then Odo raised the question around it. So what happens is that when you initialize a neural network, let's just say that particular weights really don't have they don't have inherent meaning. And if you initialize multiple times, the weight at a particular point may not be capturing the same meaning as the weight at that same weight at that particular point in a different neural network. So you can't. It's hard to average models that come from different runs, because in that case you'll be averaging models that have, let's say, their weights will have learned different things, so there'd be a mismatch. So you can only use parameter averaging when you have models that are from the same run. But yeah, we found ensembling works a lot. It's really used a lot on this guy Cargo, because you can remove the bias that one model has learned and improve your accuracy. Then there's stacking, and stacking is a little different from ensembling in the fact that in ensembling everybody gets access to the data set, everybody makes a prediction. In stacking, what we have is that the output of one model is fed to the other model before the final output is then generated. And it's very interesting way to combine different types of models. Like for example, here they mentioned where we can use a phrase-based translation model, which we then feed to a neural machine translation model. And that's exciting. I mean, the outputs are radically different, but the neural model can take these phrase-based translation models output as its own input before generating our final translation. So yeah, I think that's mostly all that I discovered this week. And they just look at some interesting work that is done in conditional language modeling. Maybe we can have everybody in this call maybe pick one of these particular papers and try and go over it over the week, and just be at the next call. We can just give us a brief what they learned, what's exciting about the particular paper. Shamsuddin.
Yeah, sure, that's cool.
Okay, so I think that makes sense.
Mm-hmm.
So we have this one. We have where they're generating from structured data to generate text, I think. Is anybody interested, or do we just pick names at random?
What do you say?
I said, how do we get people to pick papers anyway? Do we, what do I call it? Do people volunteer, or do we just pick at random? Or in order?
What are the options?
So let's look at all the options we have. We have this one where they are generating text from structured data. Structured data includes, the action, some then specifics. In this case, where they are generating, it's still the same one also. This one's also structured data, but another person, this Wiseman et al. I think these are scores for a particular sport, and they're using it to generate like a summary of what happened that particular weekend. This might be interesting to do for Premier League. Interesting to just see, just generate this type of thing for Premier League for a particular weekend. We have Arsenal 0, Man City 5. Then there's from inputs and labels, where we have an input and some kind of label, and then we're trying to generate an inflected word based on it. Oh yes, I remember this. So you have like an input, and let's say you have like a kind of label, like should it be male or should it be female, and then you try and generate like the right thing, the right sentence. I think this is used, for example, in words that are in languages where, shall I say, the masculine conjugation differs a little from the feminine conjugation. That's like French, for example. So this Zu and Newbig. Well, Newbig is also the one taking this course, so it's interesting to see his work. And then there's speaker and document traits, where you look at the description of a TED talk, as well as, you know, the author, and just try and generate a TED talk from it. This is getting difficult. Sounds interesting, Tisha. And then there's generating from a list of traits, where I think they use this one from, what's it called? For food. This particular paper looked at food, where you throw in recipe and ingredients and the name of a recipe and ingredients and try and generate a recipe. And they have a model which they call the neural checklist model. There is images to text, where we have an image, try and generate text. It's Kapati et al. There's a lot more work being done in this area these days. Interesting work. Okay. And then there is from word embeddings, where we look at from a word, we try and generate a meaning for it. And interesting. Help us see how well embeddings are capturing, you know, the meanings of words. Yeah, and that's all. So we have 1, 2, 3, 4, 5, 6, 7.
Wow.
So I think we can just go one by one. There's 4 of us on the call right now. Oh, Jayola left. That's sad. All right, that's fine then. So, Shamsuddin, which are you going for?
I'll also choose the last one, also from word embedding.
From word embedding, yeah?
Yeah, maybe, and the one before it as well. I don't know if.
Maybe because of time, you cannot speak one, because next week also will be short on time.
Okay.
So from word embeddings, we have Shamsuddin. Odun, what are you going for?
Can you, what is this one? Oh, maybe I can do this one then from images.
It's too easy for you, Odun. Okay, I've heard of.
Oh, okay, let me see what the other ones are like.
Okay. So there's this one where we generate text from a list of traits. There's one where we generate text from speaker document traits. If you want to go with images, it's fine. I won't.
Yeah, let me just do that one.
All right. How about you, Ricky? Which one do you want to go for? So you can join us again next time. Ooh. Stop you there.
That is tough for me. My internet kicked me out of the laptop, so I had to go back on my phone. I don't know why. So I'm using mobile data on my phone to try to join. It took me a while to catch up. So I don't know. African internet is something else. So and I kind of miss why you guys are picking that. I want to follow my brother Shamsuddin and say what embedding, but I'm yet to even fully grasp what you guys are trying to do with them. Because yeah.
All right. So what we just wanted is for everybody, for each of us, to pick one paper, go over it during the week, and just next week share a little something about what they learned. What we want is for everybody to just share a little bit next week about what you learned from the paper and how the author achieved this conditions generation.
Okay, please. Can you hear me?
Yes, I can hear you clearly, Ricky.
Just give me one. Just give me one.
All right, so I'm just going to note you down for speaker document traits.
Okay, speaker document traits. So I'm supposed to look for this paper by Huang et al., right?
Yes. So you just read it. Next week, you just give us, a brief summary of what you learned, how the author achieved their own condition generation. Nothing too long, maybe 3-5 minutes. Good.
Okay.
Okay, so I'll send you a text about it.
Sunday, if you maybe want to give one, and I can pick another one.
What did you say, Odun?
I said, if maybe you want to give him the easier one and I can pick any of the rest, it's fine as well.
No, it's fine. I think this one is really interesting one, and I doubt any of them is easy at all. It's so I'm going with Wiseman et al. So I can see if this can be done for the Premier League. Wiseman et al. Okay. So yeah, that's all that we have for this week. Are we in good time? Yes, we are. So we can spend the last 8 minutes looking at evaluation. So Odun, do you want to take us through evaluation?
not seen the slide before, but let's see. How do we evaluate?
Okay. All right.
So I think the evaluation here on this particular slide, we are talking about a machine translation system. So as we've understood from all of today's conversation, if I'm right, condition generation is when you are trying to generate an output based on, let's just, so the input here can be a text in a similar language, a text in a different language, it can be an image, and it can be anything else really. So you are trying to generate something, but your input is coming from like a different distribution entirely. So what they are trying to tell us here is when you are trying to evaluate this kind of models, you should use a parallel test set. So what is a parallel test set? A parallel test set is, so for instance, if you are doing machine translation, a parallel test set will be you have your input in one language and you have your output in another language. And basically, the input and the outputs you use in your test sets is going to be very similar to what you have in the training sets. Then you use the system to generate translations, and then you can now compare the translations generated by your system with the target translation you have in your test set, basically. Then there's the human evaluation side of things. So for things like machine translation, I know we have systems like the Blue Score, where we can use that to evaluate the performance. But at the same time, one of the best metrics to evaluate the performance of your model is to have a human being look at the output and tell you how good that is. So that is one way of evaluation. Scroll down. Yeah, well, they also mentioned that human evaluation is very, very manual. It can be capital intensive as well, especially when you are looking at millions of data points. So these are some conferences on machine translation where I guess they probably used human beings to.
Yeah, so for both of them, they find a way to crowdsource the annotation and the evaluation. So yeah.
That sounds like a lot of money, but okay.
Yeah, it does. So let's have Blow.
Yeah, so this is the Blue Score is another, I think this is mostly used in machine translation as well, where you are looking at the output of your model and then you have a target output as well. So high level, what you are doing with Blue is you are trying to see the number of words that you have in your output sentence, then trying to see how many of those probably exist in the target sentence as well. So there's the n-gram thing where if you are using a bigram, for instance, you are trying to look at a sequence of two words that the number of two consecutive words that exist in your output and comparing that with whatever it's in the target set. So this is very easy to use because all you have to do is just write a script for it. And of course, because language is it can be very, what's the word now? It can be very ambiguous. Blue Score does not exactly give you the best, it's not exactly the best metric. At least you can't compare with the human evaluation anyway. So one of the cons here is it does not exactly match human evaluation, and it can be bad for comparing very different systems, especially when you look at languages where there's so much inflection and sentences don't necessarily occur the same way. And there are times when you can have one input sentence in language A, but that sentence can be translated into more than one sentence in language B. So using a Blue Score does not exactly give you the best metric for evaluating those kind of systems, especially when you're looking at different.
So I think these are all newer metrics that have come out to try and address the shortfall of Blow. I haven't I haven't looked into any one of them. So I think we could also pick this one. Just what does this metric try and do? Maybe Shamsuddin, you can go with bet score. Just tell us how it works. Although you can go with Comet. I will look at Prism.
Yeah, sure. Okay.
So
now or next time?
What do you say?
You're taking the next session.
No. I think we're out of time today.
Yeah. Okay.
Against next session. Next. So that's all.
Which one should I use?
So Brett score.
Okay. Sure. So
I think Odun was Comet. I was Prism, and then there's Blue RT. So just so we have an idea. So I think we've looked at perplexity before earlier on in the course, and here again they look at how we can use perplexity to evaluate a model. Just by just run your model over your entire test set, and what is the perplexity that that it has on this held out test set. So it has the advantage that you don't have to do any generation, so it's less expensive to compute, and you don't need multiple references because of that. Because you're not comparing to like multiple references. You're just seeing how perplexed your model is when it encounters these sentences in your held out set. But it doesn't consider decoding. That's also an issue, because if there is any issue with your model in decoding, your perplexity can tell you that. It just gives you an output. So they're talking about which one to use. Which evaluation do you use? Do you use human evaluation, or do you use automatic evaluation? Interestingly, under human evaluation, there's also a number of evaluation metrics under human evaluation. That are not stated here. I know there's acute eval. There's several of them, and here I think they just talk about how do you pick? Do you go with human? Do you go with what's it called? Do you go with automatic? Most papers really will report both of them. They report both human evaluation as well as automatic evaluation. But there's also meta evaluation, where you combine the human evaluation and automatic evaluation, and there's to obtain a final evaluation metric that can really capture how your model is performing. So yeah. But mostly you report a number of metrics for your model, whether it's automatic or it's manual. You report multiple metrics just so it helps people get a better grasp of how your model is working, and maybe compare it to other existing models. So yeah, we were able to get through the slides today, and in time, really, 8 o'clock on dot. Perfect. Yeah, so does anybody want to say anything or share anything before we close out?
Nothing from me.
Nothing until we meet next week. Thank you, Tunde.
Right then, what about you, Ricky?
I don't know how to ask a JJC question. I'm trying to, I don't know. Okay, all of these things that we're doing, I think it's a bit faster now for new languages to be adopted, like for machine translation. I'm having some crazy ideas, but I don't know how effective they could be. I'm building a corpus for a language in central Nigeria called Birom. It has about 20 million people. I think about just 1 million speak it now, or less, I'm not sure. And I've been trying to build a pilot corpus for English and Birom, as it were. We don't have the JW300. So that kind of slowed me down. So I had to go and start looking for people who spoke it more than me. So I've gone to an extent, almost 1,000 sentences, and somebody thinks I could try and start doing some machine translation. And I was happy to see that you're using Hugging Face and all that, because I've been hearing a lot about it. Do you think Hugging Face can come in right now, or does it come later? Hugging Face, the GPT through. There's one Eliota GPT or GPT J6 something. I don't know. These are open source machines that are trying to imitate GPT-3. Is that far away from what I'm doing, or can it be used to help? Just asking this. Like I said, it's a GGC question. I'm still new to NLP.
I think those particular models you mentioned in particular are a little far away from your own task, because you are trying to do a translation task. And I think all the models you mentioned are what's it called? They are all generation tasks. I know that for all of them, in some cases, it was possible, for example, to try and fine-tune the GPT-2 on data in another language. I know there's at least 2 studies going on to look at how that might work out. I think there's one that is being led by, what's his name? There's one on the particular, it's being led by, I forget his name currently. On the Masikani page also, there's somebody leading that particular project for Yoruba, just to see how it might work. But I also think that you have little data, and maybe how it might work best is to find a language that is similar to Mirror, and see if they can sort of like transfer learnings from that language, and apply it to Mirror to see if it might work. But I'm really not the expert here. And well, I think that what you want to do is exciting and is brave, and you should definitely mention it as a question on the Slack channel. I'm sure that you would find people that are excited about this and that might be willing to collaborate with you or to give you pointers. Because I know that, for example, Chris Emezwe is doing something similar with another language where it doesn't have a lot of data. Also, I'm trying to see how zero shots or few shot transfer might work. So for me, I'd say raise the question on the Slack page. You will definitely find people that are willing to shed a light on the task you're working on and are willing to collaborate with you.
Okay, yeah, I'll do that. Thank you very much.
All right then.
Okay, great.
All right, I think we've had a really great session today, and I hope to see you guys all next week and hear about what you learned from those papers.
Okay, thank you, Tunde. See you next week.